Good morning, everyone. Morning, Eli. How is everyone doing on this Tuesday morning? Looks like we got a little bit more sun today, which I'm very excited about. So our game plan for today is to finish off section number 3. And that way we have a lot of time to work in section 4, which I think is the hardest section of our course. So we just have to finish up the normal distribution, talking about that continuous distribution. This is our first continuous distribution we're going to take a look at. And it should have been one that you guys covered in lab last week, I believe. Yeah, so there are no labs this week, of course. Just as a casual reminder for any of you guys that have labs later in the week, we are skipping lab this week and then starting labs fresh next week on a Monday. So yeah, so grab that normal distribution packet if you need it. Do we have any other things up and coming? When is part 2 due again? Oh, March 14th. So that's up and coming. So yeah, I would kind of keep working away at part 2 if you haven't done so. I've noticed that there aren't any uploads, nothing submitted quite yet, but that's okay. You still have a few more days to kind of work away at that. We will have, let's see, Thursday, I should be good to go for a live class. So we will plan on having a live class again, and I'll record that on Thursday. So if you have any kind of last minute questions, today and Thursday are going to be probably your last days to kind of get some questions for part 2 of the assignment if you have any questions. So yeah, so that'll be due on Sunday. We are going to have an assessment coming up for part 3. So we are going to have that end of chapter test for the probability section coming up, but let me write that test first, and then I'll see kind of how long it's going to be. Do you guys have any other major midterms, assignments coming up next week? Like if I was to, for example, schedule this test for like next Friday or something like that to be done by next Friday, would that be a reasonable thing for you guys, or would you prefer it to be like a couple weeks away? Yeah, so it looks looks pretty busy for you. Looks pretty busy next week, 15th, 17th, 23rd, 30th. Wow, it's a busy time apparently. Okay, I will keep that in mind. Maybe we'll aim for the 26th then. So basically we'll maybe try to aim it out of next week, since it looks like you have a couple of things, in today and the next week. So those are the major things. Yeah, so maybe we'll try to aim for, yeah, someone else is giving me a thumbs up. Maybe we'll try to aim for the 26th. And so basically it'll just be open. I'll try to have it finished by Friday so that it's available to you starting on the 12th. And then you just have to do it sometime before the 26th. So you just pick kind of a 1 hour period that's going to work. And that should be enough time for the review of this section. So it shouldn't be too intense. I mean, it's going to have a probability tree. It's going to have maybe a contingency table looking at probabilities in those 2 particular cases, because I think that's what's likely to come on the final exam. It'll have some questions around the distributions for discrete variables. And then it's going to have some questions based on the normal distribution, which we're covering today. So I don't think it's going to be like a super lengthy kind of test, but I do want to make sure that you have enough time to review some of those sections if you need to. Yes, I will work today on getting the review up for section 3 as well as section 4. So I'm going to try to get those finished up today and get those review sections up. Yeah, and I think that'll give you a good idea of kind of the style of question that you'll kind of expect to see on the tests and final exam as well. Cool. So yeah, that's kind of what's on the docket coming down the pipelines over the next couple of weeks. So just kind of keep working away at the data assignment part 2. And then yeah, do expect that the section 3 test is going to come up here relatively soon as well. All right, so like I said, we want to work a little bit with the normal distribution today. And this is our first continuous kind of distribution. So rather than coming at us in like discrete jumps, like a histogram, it's going to come as more of a smooth kind of curve. So what I have here at the bottom of this particular slide. So if we want to describe this kind of distribution, it's very similar to the binomial distribution. It's a symmetric, unimodal, so it has one mode, and very much bell-shaped. The only difference between the normal distribution and the binomial distribution is the binomial distribution comes as like little chunks, which is why it's more of a histogram style. The normal distribution has a continuous kind of x-axis, so it comes as more of a smooth curve compared to those discrete distributions. Now, our continuous distributions, they can have measures of center and measures of spread. And the measure of center, or the expected value for the normal distribution, is called mu, mu. And the measure of spread for our normal distribution is called sigma. So these are the two parameters that we typically use to talk about the center and spread. We use the expected value as mu. This is, we're going to see, this is essentially, we think about this as the average. This is the very centermost point of our distribution. So actually, I'm going to just maybe play the slide here. We'll get you guys into here so I can just draw a little bit on our distribution. So the measure of center always is right at the middle of our distribution. So this x value here is mu. This is going to be our centermost point, right? So the centermost point of the normal distribution always lands at the mode because it is a symmetric kind of distribution. And then this sigma value, we essentially use the square root of this sigma value to kind of talk about how spread out the data is. So there's another measure here. I'm just faking it on our curve here, but there is another measurement that we call the standard deviation that gives us some kind, wait a second, this isn't right. Okay, no, this should be sigma. This up here should say standard deviation. So if you want to change that, that would be great. So this should be the standard deviation, not the variance. This should be the standard deviation. And so the standard deviation, as we've been kind of seeing with our discrete distribution, gives us an idea of these like ranges, essentially. And that's kind of, it's this very similar idea with this continuous distribution. I have a number that represents the exact middle, and then I have a number that represents a number that I can use to make ranges. Now, we did talk a little while ago last week about the idea that as the binomial distribution, as the bins start to get smaller and smaller, and we start to get more of a continuous kind of curvature happening, that it becomes really challenging to talk about probabilities. So for a continuous kind of distribution, it doesn't make sense to define a probability for a specific number. So for example, I wouldn't be able to calculate the probability that x is identically equal to 0. I couldn't assign a probability to that. And that's because there's an infinite number of x values along the x-axis here. And if I try to define probability for every single value along the x-axis and I try to add them up, I'm going to get a number that's bigger than the number 1. So it fails one of our standard probability rules. So kind of to skirt around this problem of not being able to define probability for a specific number, what we typically do is we typically define a probability on an interval. So rather than saying something like the probability that x is identically equal to 1, for a continuous kind of distribution, we would say something like, what's the probability that x falls somewhere in between -1 and +1. So that's what this picture is showing you guys right here. And so what happens now is we think about probability as the area of a region rather than thinking about probability as a specific number. So this is the key difference, I think, between moving from a discrete distribution where I'm allowed to think about probability using a discrete number to a more continuous kind of distribution, where now I start to think about probability as area instead of probability of a specific number. In fact, the probability of a specific number happening is identically equal to 0. So might be worthwhile to jot that down in your notes. The probability of, x equals a number it has to be equal to 0, because if it's not equal to 0 and I try to add up all these probabilities, I get a sum that's larger than 100%. So this is the problem that we have to kind of figure out with regards to probability and statistics. And it was actually calculus that kind of stepped in, took the reins, and let statistics know how we could think about probability as an area. So for those of you that have taken calculus, it's connected to the area problem or the integration problem. And essentially what happens with the normal distribution is you get this really awkward looking function. And it turns out that this function, you actually can't find the antiderivative of this function. So what we need to do is we need to do numerical methods, which I know some of you, I think at least one of you is in my calculus class, and we haven't really talked about numerical methods yet. But for the sake of you that haven't taken calculus, all you really need to know is that we define area as the probability. And there's a specific function that does this for us. And this is built into our calculator. So we're going to be utilizing the calculator and basically telling it the boundary values that we need in order to calculate this area for us. Okay, so if you do have your calculator kicking around, this particular slide tells you how to get into that submenu, just refreshes your memory on how to get there. So it's in the same submenu as the Poisson and the binomial distributions. And what we're going to be playing around first is the normal cumulative distribution, so the normal CD function. So I'm just going to kind of back out here. And so I can show you, just to refresh your memory on where that is on the calculator. So let's see, let's get the calculator popped up here. So the mode button is, of course, right beside our direction arrow here. So we can go into mode, and you want to scroll down into this secondary submenu, and you want to go into number 3, which is the distributions. And both the normal PD and normal CD are here, as well as the inverse normal function. So we talked about the normal CD and the inverse normal function last week in lab. In your calculus, so of course you can use Microsoft Excel for any of these questions, and you should get the same answer as the calculator. But you may not all of you may have access to Microsoft Excel, so I do want to show you how to use the calculator as well. So let's take a look at the normal CD function. So once again, I'm going mode, down, and into the distributions. And I'm going to pick number 2. We're never going to use number 1. I'm actually not exactly sure how number 1 does any calculations. We're always going to be using number 2 or number 3, depending on what we want to do in the question. So I'm going to choose number 2 to go into the cumulative distribution function. And I just want to look at what it's asking from us. So the normal cumulative distribution wants a lower number, which typically represents the lower bound of the interval that we're working with. Okay, so let's just pretend it's 0. It wants an upper bound. Okay, so the upper x value or z value that we're going to be working with today. Then it wants the measure of spread, which is sigma. The calculator is automatically kind of set up to use number 1 because this is a standard distribution kind of number. And then it also wants the measure of center, which we call mu. So it's also automatically set up to give you 0 here as a standard value. And when you do hit equals, then the probability is going to pop out. In our case, since the upper and lower bound happen to be the same, we're essentially asking the calculator to calculate the probability that x is equal to 0. And we know based on our conversation that we can't assign a probability to a specific number. So the calculator knows that, and it returns back 0 to us. So that's what we're going to need. We're going to need 4 different values in order to do our calculations. We're going to need the lower number. We're going to need the upper number. We're going to need the measure of center and the measure of spread. So just something to be mindful of here as we start to work on a couple examples. So let's say we do want to calculate the probability that we are in between the numbers -1 and +1. So I'm going to actually just copy this and we're going to paste this over into OneNote so I can write a couple things down for you. And so a good habit to get into when you're kind of starting to work on these kinds of questions is to write down some stuff. So let's take a look at this. So this means the probability that we're in between -1 and +1. And we're assuming here that we're working with a normal distribution. Okay, so that's how I would read it out loud. I'm working with a normal distribution and I'm trying to find the probability that we're between -1 and +1. And that connects to this particular area here. Okay, so on the slide here, you have a visual that goes along with this particular question. All right, so if you ever need to draw anything, this is kind of the what we're going to be drawing. So as we start to work on examples that don't come with a picture, you might often see me trying to draw stuff because I find that the picture is helpful when we're trying to find the upper number and the lower number. Okay, so for right now, what we're doing is we're just going to take these, what we call the standard normal distribution. The standard normal distribution has a measure of center that's 0 and a measure of spread that's 1. We will eventually change these values. So you get a little bit of practice utilizing different measures of center and measures of spread. Okay, so we will eventually start changing these numbers up, and I'll show you how we can use the calculator to do that as well. So looking at the picture that we have, our lower number must be -1. This is the lowest number on that the blue interval that we're working with. And the upper number is equal to 1. So let's see, how can I do this? I am going to maybe just share my screen. That might be the easiest as we're working on some examples here. So let's see, sharing screen. And that way you can see the calculator and see the numbers and picture at the same time. So I'm still inside that submenu working with the normal distribution. I'm going to input a lower number of -1, hit the equal sign, an upper number of +1, hit the equal sign, and I'm going to keep my measure of spread to be 1 and my measure of center to be 0. And when I hit the equal sign this last time, the probability that we land in between -1 and +1 is going to pop out here. So it comes out at about 68.27%, let's say. So what does this number mean? It essentially means the following. If we have a case, so let's pretend we're designing an experiment and we are collecting data. Our data exhibits some kind of variability. And what we're assuming is that when we go to collect data, the most common and the average number that we're going to pick is 0. That's our measure of center. Okay, so that's the most common, it's the mode, it's the middlemost point of a big series of data. It's also the average number that we expect to get. So 0 happens to be like the most common number that we'll get. But we could have some variation. We could, see values of -1 when I go to collect my piece of data, or you could see values of +2. So any of these numbers along the x-axis essentially represent numbers that we could get as we collect our data. Now, the probability number that we get, which is around 0.68, tells us the probability that we go out, we collect a single piece of data, and that data is going to land somewhere in between -1 and +1. That's what this probability actually means. So I have an experiment, I'm going out to collect data. The variable I'm collecting data on has variability, right? It has some variation in what I expect to see when I go to collect stuff. And the 0.68, the 68%, is telling me that's roughly the probability that I'm going to go collect a piece of data. And when I measure that piece of data, it's going to land in between -1 and +1. Hopefully that makes sense. Is there any more kind of clarification that you want on that? Or does that help clarify kind of what this number means? It's a bit weird because, it's hard to think about going and collecting data and that data coming back to you as a -2. So yeah, we are going to change these numbers a little bit to try to make some context that make a little bit more sense. But that's kind of the lowdown of what these probability numbers actually mean, okay? Okay, I want to do a couple more calculations with the standard normal distribution. So we're going to look at a case where we want our value to land in between -2 and +2, as well as -3 and +3. So let's work away at these as well. And then this is going to bring up a really interesting rule with regards to the standard normal distribution. Okay, let's throw this calculator over here for a hot second. And what I'm going to do is I'm just going to go through and I'm essentially going to start listing the things that I need. So I have the picture already. I don't need to draw anything. What I do need to think about is, what are the lower numbers? What are the upper numbers? And we're going to keep our measure of spread and measure of center equal to 1 and 0. So we're going to assume here that we're still working with the standard normal distribution. Okay, and the only thing that's really changing here is now my lower number is going to become -2 or -3, depending on the question here. And my upper number is going to become 2 or 3, +2 or +3, depending on the question. Okay, so once you're happy with that, essentially, if you hit the equal sign here, it'll just go back to where we started. So now we can just alter the lower number to be, let's say, -2. We can alter the upper number to be +2. And then we can keep the same measure of spread and measure of center. And hopefully when you do that, you get around 95.44%. I think I forgot to fill in my final answer for the last one. What did we get here? About 68%? So 0.6827 or something like that. Okay, so essentially, like looking at this picture, another way we can think about the probability is that of all the area that we have underneath this curve, about 0.9544 is shaded in. About 95% of my picture is shaded in. So that's another way you can interpret this, but interpreting it as area instead. Okay, and finally, let's do this last one with 3 and -3. So just switching up our lower and upper bounds. Ba-boom, ba-boom, ta-da. And I get about 99.73. So for the standard normal distribution, these particular 3 ranges actually define a rule for us with regards to probabilities. So this is a really important rule. We call it the 68, 95, 99.7 rule. I know it has a very thrilling name. And it's given here on the next slide for you guys. So if you take a look at this next slide, the 68, 95, 99.7 rule is essentially a way for us to kind of know how much data is going to fall on specific intervals. So about 68% of the data that I collect should fall between 1 standard deviation above and below the center. So in other words, when we go to create a range for our data, 68% of our data should fall within 1 standard deviation above and below the middle. Okay, we've also shown that if we were to go 2 standard deviations above and below the middle, about 95% of our data should fall inside that range. And then finally, if we were to go all the way out 3 standard deviations from the middle in either direction, about 99.7% of our data should fall on that particular interval. So what we're going to be doing with this kind of rule is we'll use this a lot in chapter 4, where we want to go to create some number and we want to get a sense of how often that number is going to land in a particular interval. So that's how we kind of utilize this idea. So for now, you just need to know about how much data lands within 1 standard deviation, about how much data lands within 2 standard deviations, and about how much data lands within 3. And I'll show you the application of this particular rule in chapter 4. But hopefully this gives you kind of an idea as to why we were using 1 standard deviation for our discrete distributions, because we know that a significant amount of data is going to land within 1 standard deviation from the center, right? So that's why it's helpful to look at a range of data, because about 70% is probably going to land within 1 standard deviation of the center. It's quite typical in scientific studies to do 2 standard deviations. So there's quite a big jump as we move from 1 standard deviation to 2 standard deviations. We jump almost 25% by adding in an extra standard deviation. So quite often you're going to see things like 95% with 95% certainty. It's utilizing this particular rule where they're kind of looking at this range using a couple different standard deviations rather than 1. Let's take a look at a few more examples. We are going to, once again, explicitly or specifically use the standard normal distribution so that we're using sigma equals 1, mu equals 0. But I want to calculate, maybe 5 or 6 more examples here and show you how to do some of these kind of oddball cases. So I'm just going to get set up here, and then I will share my screen in a second. Okay, what do I want to do? Let's share the screen, and we will toss the calculator out here too. We are going to need that calculator in a second. Okay, the probability that we land exactly on 0.43. Well, this is a standard normal distribution. This is a continuous kind of distribution. There's a 0% chance that's going to happen. Okay, we can't actually specifically land exactly on 0.43. And sometimes I kind of tell students to think, if you've ever played like darts or something like this, it's very similar to like throwing a dart at a dartboard. There's a 0, like if I were to like walk up there and pick a very minute specific point on the dartboard and you throw that, like there's a 0% chance that the dart's actually going to land exactly at the point that I pick on the dartboard. But what I could do is I could say something like, what's the probability that you hit the number 20, right? Anywhere in that like little fan where the number 20 is. It's possible to talk about the area on the dartboard as a probability, but it's really hard to talk about landing on a specific point. Even a bullseye has a defined area, right? So that's kind of how I think about probability for continuous distributions. It's really impossible to throw a dart and land on a specific point, but I could throw a dart and land within a region on the dartboard. So that's why number 1 is 0. Number 2 and number 3 are actually going to have the same probability. So let's think about number 2. So I'm going to do a little bit of work down here for number 2. I'm going to draw my normal distribution. And let's see, I'm going to plot 0 because I know where 0 is. 0 is exactly in the center. And I'm also going to plot the number 0.43. So that's going to be a little bit bigger than the number 0. Okay, so maybe over here somewhere. It could be a little bit, you can put it closer to 0 if you want, but I want to make sure that I can shade in this region. So in green, I'm going to go ahead and I'm going to shade in the region that is less than or equal to 0.43. It should be everything in here. So we're trying to calculate the area that we land inside this region. Calculate the probability that we land inside this region, sorry. So for number 2, we're going to need a lower number. We're going to need an upper number in order to utilize the calculator. We know that the standard deviation is 1 and that the measure of center is 0. Okay, one of these numbers is very obvious. The upper number, I think, should be 0.43. However, we don't have a lower number, right? So there is no lower number. So we have to get a little creative on how to utilize the calculator. And it goes a little something like this. So here's the standard normal distribution, let's say, right? Numbers that are on the other side of the number -3 have very little probability that we have to work with. So maybe you could imagine that if I extended the x-axis even further to say like -10 or even -100, that our curve would be so close to it that there really isn't any area there. Like the area is so tiny that it's not going to affect our overall answer. So what we're going to do to kind of cheat the system a little bit is we're going to put in a large negative x value, and then the calculator is basically not going to be able to add any area. So I would say in this particular case, we could go with like -100. We could probably even go with -10 and we would get the same kind of answer here. But let's take -100 just to be safe. Okay, so we use a large negative value here to represent our lower. And so this is a strategy that we use if we have a less than or a less than or equal to sign like we do in number 2 and number 3. All right, so let's pop out the calculator. We have a lower number. We're going to put in -100. Our upper number is 0.43. And we'll leave the standard deviation and average the same. So we get the number of the devil, apparently, 0.6664. That's how I think about stats. Stats is the devil. Okay, I had already mentioned that number 2 and number 3 are going to have the same probability. Can any of you maybe explain why that's the case? Like these symbols are different, right? Right, like one is less than 0.43 and one is less than or equal to 0.43. So why is it that these two things have the same probability? Why is that?
Is it since number 1 gives us a hint that there can't be any that equal 0.43, so therefore all of them have to be below 0.43 anyway, so.
Yeah, exactly. That's the best way to think about it. It's impossible for us to define probability exactly at 0.43. So whether or not we include it in our calculation doesn't really matter. Yeah, so that's a really nice way to think about this. So they have the same probability because it doesn't really matter if we include 0.43 or not, because we know the probability of landing exactly on 0.43 is 0. Okay, so what I'm saying here is like we already know from number 1 that probability is 0. So we can either include the endpoint like we do in number 2, or we could not include the endpoint like we do in number 3. It doesn't really matter. We'll get the same probability anyway. So most of the time when we're doing examples, we don't usually use the less than or equal to symbols with continuous distributions because the endpoints don't really matter. We usually only use the less than or equal to symbols when working with discrete distributions because it does matter with discrete distributions. Okay, see if you can calculate this last one. What's the probability that x is going to be bigger than 0.43? There's a couple different ways you can do this. You can be sneaky, or you can do it the long way. It doesn't really matter to me. I will draw a picture for you, though, as you're kind of thinking about this. So here is 0. Let's say here is 0.43. And in green, we want everything bigger than 0.43, which is somewhere out here. So I'll do it the long way. We would take our lower number to be 0.43. We could take our upper number to be something really big and positive, like the number 100, for example. Okay, and keeping the standard deviation and average the same. So let's see, what do we get here when we take our lower to be 0.43, take our upper to be 100, and leave everything else the same? We get about 0.3336, let's say. And what I want you to notice is there a relationship between these two numbers? What's the relationship between these two numbers? Do you notice that they add up to 1 or 100%? Yeah, so Eli had just mentioned that in the chat there, so you'd kind of seen that. So this is that property of complementary things adding up to 100% still works for continuous distributions. And we do use this every once in a while, this idea of if something's hard to calculate, sometimes we'll do 100% minus the thing that's easier to calculate. So just be mindful of that. So the complement property still holds true with continuous distributions. Okay, and like I said, the calculator is usually really good at skirting you around having to use the complement property. However, if you are reading the textbook doesn't use our calculator. They use what are called a normal probability table. So it will use the complement property a lot more because it's using the table to find these decimal numbers rather than using something like Microsoft Excel or using something like the calculator. If you have the calculator, I always just recommend practicing with the calculator because you don't have to worry about the complement property. You can kind of sort it all out based on drawing a picture and figuring out your upper and lower. We will have to use the complement property a little bit more when we're working on the inverse normal distribution, which we will talk about in a few minutes. So let's do a couple more examples, some more varied examples, just so that you get a good handle on how to utilize the calculator for some of this stuff. Okay, I think I'm still sharing my screen. Yeah, perfect. Okay. Let's do 3 more examples. Like I said, we'll try to draw a picture and we'll try to calculate what we should be inputting for the upper and lower numbers. So I'm just going to maybe draw the pictures over here on the right-hand side. Okay, remember, again, we're just going to assume that we're working with the standard normal distribution. We'll work with some varied numbers in a minute. So the standard normal distribution always has a middle point that's equal to 0. And our next goal is to try to get these other boundary numbers onto the diagram. So I need to be able to plot negative 2.14. That's going to be somewhere over here, right? It's going to be less than 0. Okay, and in green, I want to shade a region. Am I going to be shading this region or this region? Do I want stuff that's to the left of negative 2.14 or stuff that's to the right of negative 1.24? And that's the question you want to ask. We want values that are less than negative 2.14. So we want everything way over here. Okay, now that you have an idea of what that picture looks like, the next goal is to try to get the lower and upper number that we need in order to utilize the calculator. Okay, we're going to assume that the standard deviation is still 1 and that the average is still 0 for these questions. Okay, so maybe I'll just write that up top. So we're always going to take center to be 0 and deviation to be 1 for now, just so that you get a little bit of practice with the standard normal. Okay, where is negative 2.14 going to go? Is it going to be our lower number or our upper number? Well, I mean, the picture hopefully makes it obvious to you that negative 2.14 should be the upper number of this green region. And since there really isn't a lower number, let's take a large negative number like negative 100. Oops, I can't, where can I put this so that we can see stuff? Here's probably okay. All right, so our lower number, let's take negative 100. We have an upper number of, negative 2.14. Can I get that? I can't get that minus in there. Negative 2.14. Okay, and we'll leave those the same. And so I get a probability of like 1.62%. So 0.162. And what I always like to do is kind of like look at the probability that I get, which is about 1.6%. Look over at the picture and be like, does that make sense? Yeah, it kind of makes sense. I mean, negative 2 is pretty far away from the middle. So yeah, I think 1.6% makes sense for this particular example. I mean, if I had got an answer that was like 62%, and I look at the picture, I know I'm kind of like out to lunch because the region that I've shaded in is much smaller than what 62% would look like. So sometimes you can kind of like kind of fact check your answer and see if it makes a sense. Okay, let's take a look at this range. So this is the probability we land in between negative 1.32 and 0.4. So let's put the upper number in, 0.4. We'll put our lower number in, negative 1.32. And we want the probability that we're going to land in between these two numbers. Since two numbers are given in this particular case, we know that the lower number is going to be negative 1.32 and that the upper number is 0.4. So this one's, I think, a fairly straightforward kind of computation. I will just maybe move that over here. All right, negative 1.32 and 0.4. Okay, we get about 56%, which doesn't seem unreasonable based on the region that I've shaded in the normal distribution on the right-hand side. So let's take 562, so 0.562. I'm always going to be taking 4 decimal places in case we need to convert these to a percent. So always take 4 decimal places, and that way you can convert this to a percent that has 2 decimal places if you need to. So 4 decimal places is what we want when we're working with the normal distribution. So just be mindful of that. Okay, last one. Let's give a rough picture of this one. We need 1.02 on here. And we want to shade the region that's larger than 1.02. So anything to the right of 1.02. Okay, so in this case, 1.02 looks like it's going to be the lower part of the interval we're working with. And we're going to take an upper that is, I don't know, maybe a large positive number like 100. And we can pop the calculator up and put those values in and get some kind of answer here. All right, so let's see, we have a lower number of 1.02, an upper number that's really big and positive, and we keep those the same. So we get about 15.37%, which again, doesn't seem unreasonable. I mean, it should be less than 50% based on the picture that I have. So that seems okay to me. So 1537, let's take 1537. Oops, 1539, I guess is what it should be, not 37, 1539. Okay, so that's a little lowdown on how we calculate probabilities using the calculator for the standard normal distribution. How are you guys doing? Do you have all that all copied down? You're ready to go into some non-standard normal distributions? Okay, so I see a thumbs up, 2 thumbs up, perfect. So like I was saying earlier, most of the time when we go to collect data, we're not really going to be collecting data that has a measure of center that's 0. Okay, so for most of the time, we're going to get something that's not standard and normal. We're going to get something else, but it's still going to be a normal kind of distribution. So in other words, maybe I go out and I collect data on the heights of Canadian females, right? So that data is going to be normally distributed, but obviously the average or the center of my data is not going to be 0. It's going to be somewhere else. I don't know what the average height of a Canadian female is, maybe somewhere around like 5 feet. Don't even ask me in centimeters, don't know. 5 feet some odd inches, right? So I'm going to get a measure of center or an average that's, somewhere around 5 feet and some odd inches. It's not going to be 0. So the question is, how do I utilize the calculator, right? How can we kind of move our normal distributions around with this understanding that the center might be something different and the measure of spread could be something different too. The standard deviation we get from collecting data on the heights of Canadian females could be different than 1. It may not be 1. In fact, it's probably going to be something else. So luckily, with Microsoft Excel and with the calculator that I've requested you have for this class, there's not too much we have to worry about. However, I do think it's important to show you the theory on how we standardize a normal distribution. So, and it all kind of comes back to this big calculus problem. And the big calculus problem is finding the area underneath this function f of x. As the average and standard deviation start to change when I go to collect data, that's going to change f of x a little bit. And it's quite hard to calculate the area underneath this curve. It's really hard. So what was typically done in the past was to take one of these non-standard distributions and somehow convert it back into the standard normal distribution. And we had charts. So we had a chart that listed all of the different probabilities for lots of different values of x. So that was common practice, we call this standardization. We would look at the average and the standard deviation that we had for our normal distribution that we were collecting data on. We would convert it by using the formula here at the bottom. So we would take z, we would take it as equal to x minus mu over sigma. That would convert our variable to a standard normal variable, and then we could use the charts at, say, the back of a textbook in order to calculate the probabilities. So that was kind of commonplace before we had access to things like Microsoft Excel and things like the calculator. So essentially, what we measure here is if we're looking at calculating a probability, we're looking at a specific X value on this range. And what we can do is we can calculate how many standard deviations that X value is away from the center. And by standardizing, we end up getting a number that's in between, -3 and +3, let's say, or it could be bigger too. But anyway, we end up getting an X value that kind of lands somewhere on this X range, essentially within the X range of the standard normal distribution. So that was a very common thing to do. So if you see the textbook saying something like finding a Z score or standardizing the variable, this is what they're trying to do. They're trying to figure out how many standard deviations is this number away from the center. And then they're trying to apply that number to a standard normal distribution. And what we're going to try to do from now on in the notes is we're going to try to use capital Z for the standard normal distribution and capital X for a non-standard distribution. So I'm going to try to do that from now on so you kind of know which is which. So I do want to give a couple examples to you of how we could standardize something, because I mean, it could very well come up that we do need to use this standardization idea. But for the most part, standardization, we don't really need to use it that much anymore. We need to use it maybe once or twice, but for the most part, the calculator or Microsoft Excel can deal with this problem now. But there's a lot of, I don't want to say mean things, but there's a lot of like old style statistics teachers that still want you to know how to standardize lots of things. So let's do a couple examples anyway, so you know how to standardize stuff just in case. Alrighty, let's just do it right in here. So in this particular example, we have a normal distribution. So we're going out, we're collecting data, and the data that we collect has an average of 3. Okay, and a standard deviation of 5. Okay, so this is a bit more realistic. I go out and maybe I collect data on, I don't know, the average number of caterpillars I expect to see on some kind of bush, right? And the average is 3, but the standard deviation is 5, right? So I could get, 70% of the time I'm going to get somewhere in between like 0 and 8. So I think this is a more realistic kind of distribution, right? Something that's positive, has quite a wide measure of spread. This is a very common thing to see. So what we'd like to do is, let's say I go out and I look at one of these plants and I get X is equal to 2. How can I standardize X is equal to 2? In other words, how does X equals 2 match up with something from the standard normal distribution? So if I ever see the word kind of standardize this value, or sometimes you see the word Z score, it wants you to go through this procedure of calculating a capital Z value. So the capital Z value that goes along with our X is equal to 2 is given as this number minus the mean divided by the standard deviation. So for us, our standardized value is going to be 2 take away 3. So 2 minus the average divided by 5. Okay, so 2 take away 3 is -1. And if we divide that by 5, we get what? -0.2. So what does this -0.2 mean? This -0.2 means that the number 2 is under what we would expect to see as the average. It's less than the average. And in fact, it's 0.2 standard deviations away from the middle. So that's how I interpret this number. It's a negative number, so that means that the number we're looking at is less than the average. And in fact, it's about 0.2 standard deviations away from the center. By the way, what is 0.2 of a standard deviation? What's 20% of 5? I think that's 1, right? So 0.2 of a standard deviation in our example is 1, right? So x equals 2 is 1 step away from 3. That's how we're interpreting this. It's 0.2 of a standard deviation away from the middle. Okay, I might need a little bit of room to show you everything I would like for this second part. So just give me a second to get set up for that. Okay, where is Zoom? Dear Zoom. There you are. Okay, let's do a screen share. Okay, so we should be back and in action. Okay, I'm going to move the calculator out here too. So now what we want to do is determine the probability that x is less than 2. So I would like to show you in kind of the more classical approach. And so we'll call it classical. What period are we in right now? New age? Technology age? But I'll show you anyway. I'll show you both ways. So I do want to show you how to calculate this using the standard approach, the standardized approach. And I'll show you how to do it in kind of the very simplistic way, just utilizing the calculator as well. So the classical way, it would be 1 to find the z-score. Okay, which we have already. So z is equal to negative 0.2. And then what we're going to do is we're going to plot this on the standard normal distribution. Okay, remembering that our measure of spread in this case would be 1 because it's standard and normal, and our measure of center would be 0. Okay, we want the probability that x is we want the probability that x is less than negative 2. So that corresponds to the probability that z, our standardized score, is less than negative 0.2. Okay, so we've converted x into a z so that we can utilize the standard normal distribution. And we're interested in this probability. Now, normally we'd go to a table, but we can use the upper and lower idea on our calculator to get at this probability. So we know that the lower number here should be equal to, a large negative number. The upper should be negative 0.2. And then because we're using the standard normal distribution, we have the following values for sigma and mu. Okay, so I'm going to go ahead. I'm just going to finish this up using the calculator. Upper would be what? Negative 0.2. And we keep that the same. Okay, so the probability that our number, our z-score that we get is less than negative 0.2. What did we get here? Is 0.4207. Okay, so about 42%. So that would be the old way, right? Convert my X value to what we call a Z-score or a standardized score. Then we think about the probability on the standard normal distribution. So what we've kind of been working on already. Now I want to show you that there is a really nice way we can kind of skip having to standardize. If all we want is the probability, we can actually skip that. Okay, I still like drawing the picture. So I want to show you how the pictures differ. So if we skip standardizing, what we're going to be using is we're going to be using our normal distribution, which has sigma equals 5 and mu equals 3. Okay, so just be mindful of that here. So we're going to be taking sigma equals 5, mu equals 3, because we haven't standardized x equals to 2. Okay, so I'm going to be putting 3 here as the measure of center. And we need to figure out where x equals 2 is on this picture. So that's obviously going to be somewhere over here. Okay, so the key here is to use mu and x on this picture. Over here, we're using mu equals 0, the standard. Sorry, I should say mu equals 5. And here we use z is equal to negative 0.2. Having a rough writing day today. Okay, try again. Negative 0.2. There we go. So here we want to use mu equals 5, or 3, and x equals 2. Okay, because we haven't standardized it. We use the average given to us and the x value given to us. We want the probability that x is less than 2, so that's going to correspond to this region shaded in here. And then we can use the lower and upper numbers that we think make sense based on this picture. Okay, so lower, again, we can maybe take as like negative 100. That's pretty big. Upper number, let's take as 2. And then because we haven't standardized anything, we're going to take the standard deviation and the mean that are given to us at the start of this question. Okay, and I'm just going to pop the calculator over here, let you guys kind of get caught up. Okay, and let's have a crack at this. So let's take the lower number to be negative 100. Now our upper number, we're going to change to 2 because we haven't standardized anything. And again, we're going to now change our sigma from 1 to 5 because we haven't standardized. And again, we're going to change our measure of center, our mean, to 3 because we haven't standardized. Okay, but I should be able to put all of those into the calculator, and the calculator is going to spit out 0.4207. So we know that the probability that x is less than 2 is 0.4207. And what you should notice is that these two probabilities come out to be the same. So this was the point of doing standardization back in the day, because the theory said that these two probabilities should come out to be the same. If I know how many standard deviations my x value is away from the center, I can use that inside the standard normal distribution to get the probability from a table. But I don't know, we have the calculator, we have Excel, we don't need to do that anymore. So my preference is always going to be to use the faster method if I don't need to standardize anything. So I'm always going to be kind of using the secondary method. You know, if the standard deviation and the center are given to us already, why would I go through this process of standardizing, then using the calculator, when the calculator will just do that standardizing for us? Okay, hopefully that makes sense. I did want to show you both ways because the textbook may show you the classic way, which is to find the z-score and then think about how this corresponds to the standard normal distribution. So that's what we're using over here. Okay, but my preference, if I don't need to calculate that standardized value, is just to use the non-standard distribution because the technology can handle it. Okay, so once again, I would like to just kind of pause for a hot second and make sure you guys are happy with that. So either just throw me a little thumbs up or a little yes in the chat, whatever your preference might be. Okay, so 1 thumbs up, 2 thumbs up, 3 thumbs up, great. So let us move back into maybe a little word problem. I think a word problem will do here. Okay, so let's suppose that, that's funny that we were talking about heights of adult females. I didn't know, I forgot that this was the example in here, but suppose we go out and we collect data on the heights of adult males in Canada, okay? And we know that the heights of adult males are normally distributed, and we're going to assume that they have a mean of 69 inches, and a standard deviation of 420, just getting 2.4 inches. What is the probability that a randomly selected person is going to have a height somewhere in between 62 to 70 inches? Okay, so if you come to an example like this and we're thinking about probability of a normally distributed variable, what we need, what we're hoping we get, is the mean and the standard deviation. If I get the mean, the standard deviation, and a range, I can program that into the calculator, and the calculator is going to toss out a probability number for us quite quickly. So I'm just going to go through, I'm going to highlight some of the important things that we're going to need here. Okay, obviously the idea that it's normally distributed, this is important. Because if this variable was not normally distributed, we wouldn't be able to use the normal cumulative distribution function. But the other kind of important thing here is we have our standard deviation of 2.4. We have our average of 69. And then we're curious about heights that are between 62 to 70. So we want to calculate the probability that we land somewhere in between 62 and 70. Okay. So that's really the important information that we can grab from this particular example. And then we should be able to put it all together. Okay, I'm just going to draw a quick little picture here just in case you want to see what that looks like. So we have an average of 69 inches, and we are looking for values in between 62 and 70. It's a little bit tight there, but we're essentially looking for the probability that we're kind of inside this strip somewhere between 62 and 70. Okay, so seeing that picture, we kind of obviously, hopefully should see that the lower number we need is 62. The upper number we need is 70. And we have a measure of spread of 2.4 and a measure of center of 69. So basically, we just want to throw that into the calculator, see what the calculator is going to spit out for us. And we're good to go. We don't need to standardize anything here. And I get about 65,6598 when I round to 4 decimal places. So that probably have about a 65 or a 66% chance that we're going to kind of land in between 62 to 70 inches. That seems fairly reasonable considering that the standard deviation is 2.4 inches. Yeah, that seems pretty reasonable. I mean, if I had calculated this and I got like, I don't know, it's hard when it's a little strip like this, but 62 is pretty far away from 69. 70s, a little bit closer, but yeah, how many standard deviations is 62 away? It's like, that's a difference of 7, right? So 62 is quite far away from the middle. So yeah, 65% kind of makes sense to me. I'm happy with that. Let's see, what is it actually? I got 65.95. 65.98. Yeah, 65.98 is what I got as well. So that's good. That's great. So there you go. There's a word problem. I think that's a very kind of common or typical kind of word problem you should expect to see on the final exam. And hopefully that's fairly straightforward in what we do, right? You draw yourself a little picture just to make sure you know what the upper and lower numbers are. The mean and the standard deviation are given, and then you just kind of toss everything into Excel or into the calculator. Okay, so for the last little bit of the course, I'm just going to pop out here so that I can keep an eye on the time. For the last little bit of the course, I just want to talk about how to do the reverse. So what if we have the probability number and we want to calculate the corresponding X or Z value? So we have the probability number over here as like about 92.79, and I want to calculate down here kind of, where am I along the X or Z axis? So this problem does come up quite a bit as well. And to solve this particular problem, we use the inverse normal distribution. And the three things we need to program into the calculator are the area. So the area here meaning the probability number. And that area needs to be expressed as a decimal number. And we usually try to get 4 decimal places here. And then it's going to need to know the corresponding standard deviation and mean as well. Okay, so let's work on a couple practice questions using the calculator and trying to figure out where the X or Z value is. So let's try this one. I am just going to, let's see, I'll do a screen share and pop up the calculator so you can kind of see how I'm thinking about this one. So I do have to go back into mode and I have to scroll down back into the distributions because I'm using a different kind of function inside the calculator. I want to use function 3, which is the inverse normal. This calculates an X or Z value for us if we happen to have the probability number. Okay, so in our case, we have the probability number. It's 0.9279. Okay, and then it's going to ask us, hey, what's the standard deviation? This is a standard normal that we're working with at the moment. So standard normal would be 1, and standard normal measure of center would be 0. Okay, and then it's going to pop out a number. So in this case, it says the number that we're looking for is about 1.46. So I'm just going to bounce into the current slide here and just kind of jot some stuff down. I think it's still on screen share, so you guys should hopefully still be able to see everything. So we took the area equals 0.9279. We took the measure of center and measure of spread to be 1 and 0. Okay, and we got Z is equal to 1.46, right? 1.46. Okay, and that's the value that should go over here. So this is the number down here that we're looking for. Now, one thing to be mindful of is, just like Microsoft Excel, the calculator is only able to do the less than symbol. So if I ever need to calculate the probability of something being bigger than a number, I do have to use the complement property. Actually, maybe that's important enough for us to jot down right now. So note, calc only does the probability that X is less than something If you want probability that x is greater than something, we can set that equal to 1 minus the probability that x is less than something. Okay, so the idea here is we use the complement property if we need to. This will be the greater than symbol. And this over here is the less than symbol. So I do want to work through just a couple more examples here before we hightail it. And then we'll maybe finish off on Thursday. Yeah, Thursday we can do a little kind of recap and review of some of this stuff. Actually, you know what? It's already 17 after. Why don't we save these examples for Thursday? So we'll do a couple of standard examples. We'll do a couple of non-standard examples, and then we'll take a look at a word problem as well. So we'll try to finish all this up on Thursday, and that way you get a little bit of a review of this, and we can do some more examples if you guys think you need some more examples. Yeah, so I think that should be good for today. So if there's anything you guys need, just let me know before you go. Otherwise, have a great rest of your day, and we will finish this chapter off on Thursday, 8 o'clock. Be there. You're welcome, Jordan and Lex. Have a great morning.
Thanks, Brian. See you later.
You're welcome, Christian. Cheers. Yeah, take care, Vivian. Thank you. Have a good one, Eli.